Hello, everybody, and welcome to this session on the new Fused Location Provider. Thanks for joining us here in Mountain View and also folks on the live stream. My name is Michael Angermann. I'm a software engineer here at Google, right across the street. And my job is to improve location on Android.
Hello, everyone. My name is Martin, and I'm as well a software engineer in the Android location team here in Mountain View.
Thanks. It's great to see that so many of you have so much interest in good location. And that's no surprise, because location is super important. It's used in many amazing apps, and all these apps make our life so much easier. So I would like to ask for a quick show of hands. All of you have traveled to, or many of you have traveled to Mountain View, and who of you has used maps this week to find your way? I have. Okay, I see 2 people who haven't, but everybody else has. That's great. And who of you has used a ride-sharing app? Okay, okay, that's a lot. Who has actually exercised and used a fitness app this week? Okay, this is getting fewer. But I think we see location powers all of these experiences, right? And I know that I'm preaching to the choir here because most of you probably showed up because you carry responsibility for building location into your apps. And I would like to take a moment and talk about one really important service that uses location. And in contrast to the other ones, I really hope that none of you had to use it recently. But in fact, I think it is the single most important service that uses location. And I'm talking about the Android Emergency Location Service, or ELS. When you call 911, it's critical for first responders to know where you are. But if you've ever done it, it's really difficult to describe your location, especially when you're stressed. So when we order a rideshare, we don't have to describe our location. We just send it off with the app, and the car comes to where we want it. And that's obviously the solution we would want for emergency services as well. So it's very easy. We send the location to the emergency services, and when we call in an emergency. And it's exactly what ELS does. It sends the location via HTTPS or SMS. ELS is already deployed in 18 countries, and it's growing very fast. There is a really, really good talk that I would like to recommend. It's happening at 2:30 today at stage 1. It's by the same team. It's different speakers, and I highly recommend to watch it. It's really good. So Android provides a lot of choice to developers, especially when it comes to location. You can choose to get location from network location, straight from GPS. You can get it via Location Manager or the Fused Location Provider. And over the next 35 minutes, we will provide you with all the background that you need to make a really informed decision to what's best for your app. And in particular, we will answer 3 questions. First, what is good location? Second, how do we at Android make good location? And third, and probably most importantly, how can you use that location in your own apps? Let's start with the first question. What is good location? Well, that's easy, right? It needs to be accurate, obviously. But it turns out it needs to be a lot more than just accurate. And choosing the right source of location is like choosing the perfect wine that goes with a good menu in a restaurant. And winemakers work really, really hard to make their product better every year. And we do the same thing with location. We really strive to make location better with every release. And like winemakers, we get really happy if true connoisseurs who know about it appreciate that location. And this is why we want all of you to be true connoisseurs of location and have all the information that you need to judge it and make the right decision so you can build what best fits your app. And we found these 4 properties that good locations should have. I said it's not only accuracy, but accurate is in there. But the other ones are equally important. Smooth, ubiquitous, and instant. And let me explain each one of them in a bit more detail. And let's start with accurate. When people talk about location and pitch a new sensor or a new algorithm, they often give just one number. They would say, our accuracy is 7 meters, or accuracy is 25 meters, or our accuracy is 1 meter. But what does this actually tell us? Usually this number is supposed to reflect the typical error, or distance between reported and true location. And we can use statistical measures such as the mean or the median of an error distribution to compute a value for that value. And again, this number tells us something about the typical error. But that's not the whole story. You definitely want to know how big the error can get under difficult situations. And that's captured by what we call the tail error. And depending on the specific needs of your application, that may even be more important than the typical error. And if you run your own evaluations, of course, you can look at an entire error distribution like what's shown in this diagram here. But in most cases, typical and tail error can give you a fairly good picture. And just to quickly talk to what we see in this illustration, there are two algorithms, A and B. And A does really better on this typical error, but B does better on the tail error. And again, it may depend on your application what's best for you. Smooth. Good location is smooth. Users don't jump, so locations shouldn't jump. And it's really annoying to see a blue dot crisscross the screen. And when it happens, users complain about it. And there are a few things that can lead to jumps. And in the previous slide, I talked about accuracy. And surprisingly, there is a trade-off between accuracy and smoothness. And chasing the latest measurement can actually improve accuracy, but it can be very detrimental to smoothness. It can lead to jumps. And that's what you see in this example on the top. The green line there shows a ground truth location, and the red line shows the output of an algorithm that aggressively chases the latest measurement. And we see how much it jumps. This is not a pleasant experience. This is not what we want. On the bottom, we see the output of an algorithm that puts more emphasis on smoothness, and it's a much better experience. It's just to show the differences between these two. Also, quickly talk about transitions, because they're also a major source of jumps, and they come in various forms. Users transition from outdoors to indoors, and we'll talk about this a little bit later, and when we see what this does to our input signals. And users transition from driving to walking, or they take their phone from their pocket in hand. These are all transitions that we have to handle and that we have to perform well. Next is ubiquitous. And ubiquitous means definitely coverage across space, such as different countries, regions, or cities. But it means more. It's not only across space, it's also across different environments, such as indoors or outdoors, type of movement, whether you're moving using wheels or whether you're moving using your feet, and the type of carry, such as in hand, in pocket, in a purse, or in a cup holder in a car. And just think about an example of ride-sharing. So we want to bring the passenger and the driver together, right? And think how different their situations are. The driver is in their car on wheels, outdoors with the phone on the dash. And the passenger is indoors on foot and probably has the phone in their pocket. And location has to work for both of them. And I almost forgot, we don't endorse using a phone while skateboarding, and please wear a helmet. The last property of good location, it needs to be instant. And what do we mean by instant? First, we mean no wait. If you can see this orange arrow that points on this map, it points to a gray dot. And that's not a happy sight. That means we haven't been able to produce or compute a good location, therefore we are showing a gray dot. And a user needs to wait for this, or an app needs to wait for this. This is really not what we want. So instant means we are able to rapidly compute a location and don't have to show that gray dot. Second, no lag. And that's also super important. Imagine if we had a really good locator and it could produce the most accurate location while driving on a highway. No error at all, but it would always be 5 seconds late. A lot of users would miss their exits and they would be really unhappy with us. So good location also needs to be on time. Okay, I think we now have a really solid foundation to evaluate good location. And I do hope that thinking along these 4 properties, accurate, smooth, ubiquitous, and instant, comes in handy when you design location into your apps. And we now get to dive a little bit deeper and talk about how we make good location in the FusedLocationProvider. Android provides a long list of really great sensors. There are the radio-based ones that we see on the top, such as GPS, Wi-Fi, or cell. There are the inertial sensors, such as axle or gyro, as well as magnetometer and a few others. And each of these have very unique properties. Now, the question is, which one should we use to make location? Let's start with the one on the top. And in this list, GPS is actually the only one that has been specifically designed to provide location. And GPS performs really great outdoors and in open sky conditions. But whenever GPS signals are blocked, such as in a building, GPS performance suffers a lot. So to show this, we created this illustration. What do we see here? The blue line shows GPS location accuracy over time. And this would be a user who starts outdoors and their accuracy from GPS is really good. That's that blue shaded area on the left. And then that user enters a building, that's that red shaded area, and the location accuracy from GPS really drops because the signals are blocked. There's not much GPS can do. It drops really to the floor. At some point, user exits that building, and the accuracy gets back and is really nice again. So we are really fine outdoors, but we do have a problem indoors here. Luckily, we can also compute location from Wi-Fi. And Wi-Fi shows really the exact opposite behavior of GPS. Its quality is really poor outdoors, but it's surprisingly good indoors, and that's because this is where a lot of Wi-Fi access points are. And this helps us to create that really accurate Wi-Fi location. So if we combine these two, we get this orange curve. And that's already much better. It's really good. Like, we have turned a situation that was really poor into something that's much better. But I'm sure you noticed there's still this gap. And unfortunately, this gap is right at the moment when this person exits the building. And this is when we would really like to provide good guidance. So we need a good location for that. And it turns out that we can use inertial sensors, namely axial gyro plus a magnetometer, to bridge that gap. This is this green gap filler here, and I'm going to explain that in a moment. So let's look at what this buys us. We have turned a really rough location experience into actually good location by combining multiple servers. So the question that we ask is really the wrong one. It's not about which one to use, but how to best combine them. And the technical term for this combination is fusion. And this is obviously why the FusedLocationProvider is called the FusedLocationProvider. And we have two main motivations to perform fusion. First, and that's the most obvious one, is to improve the quality. So make it more accurate, smooth, ubiquitous, and instant. But that's not the only reason for it. We have another opportunity from fusion, and that's we can improve the battery life. How do we do this? Well, fusion allows us to turn off the sensors that are not very effective in a situation. And, oops, I'm sorry. So in this particular case, we would turn off Wi-Fi while outdoors, and we would turn off GPS while being indoors, without any detrimental effect to location quality, and this saves us a lot of battery. Okay, let's now look at how this fusion happens in more detail. Look at our sensors again, and if we look at them closely, we can partition them actually into two domains. One is a fast domain, one is a slow domain. So GPS, Wi-Fi, and cell provide information only about once every second or even slower, and that's what we call the slow domain. In contrast, inertial sensors and the magnetometer comes in much faster, say 100 times per second. And that's why we call this the fast domain. So this partitioning allows us to apply Bayesian fusion algorithms that best fit each domain. And of course, we can perform a lot more operations per measurement in the slow domain and need to be really efficient with every measurement in the fast domain. Together, they form what we call the hybrid Bayesian fusion, and that's the workhorse of the new FusedLocationProvider. Talk a little bit about Bayesian fusion algorithms in general. So typically, they perform 2 steps or phases. One is predict, one is update. And ours is no different in this regard. Let's look at this illustration. Everything starts at initialization, say from a really good GPS measurement, as we had outdoors in this example earlier. And then we apply a model and these fast measurements to predict the user's movement. In general, this will lead to a growth of uncertainty, and we see this here. This blue dot just grows. And after a few steps, and that's to be taken literally, a new measurement from Wi-Fi comes in, and we use it to perform this update step. And we compare and correct the hypothetical positions from our prediction with this new measurement, and we get a more certain location estimate. And in general, this is what happens. An update step will reduce the uncertainty. And this is why this blue dot shrinks in this illustration. And then, after this update, we're back to the previous step, and it's predicting again from these fast sensors, and the uncertainty grows again until we get the next measurement. And what's really important about this is you will already see you really want this uncertainty to grow very slowly. That's critical. And so being good in this prediction is a key to creating that good location experience. And we will dive deeper into this now. Because the key to good prediction is understanding locomotion and applying the right models to each type. So what is locomotion? Locomotion is like the way how we move. And we touched upon it a little bit earlier. That could be on feet when we're walking or running, or it could be on wheels, like in a car, a motorcycle, a bike, a wheelchair, or the skateboard that we saw. A lot of people use location. We always have to deal with edge cases. But for now, let's look at a more typical, really well-behaved pedestrian, me. Because this is a very common case for our users. And so what we see there on the right, and I explained this, that's a top-down or bird's-eye view of a walking user. So could be me. I'm going to the back of the stage here, and I got this blue shirt for this talk. So this fits. And so imagine a camera looking at me from top down. And I'm just walking in this slight arc. Okay? This is me. This is what's shown on this slide. And we will need this later. So I had to introduce this. And remember, we said we need to be able to predict the motion between updates from GPS and Wi-Fi. And we can do this by using a technique that's called pedestrian dead reckoning, or PDR. It's a little bit of a weird name, but it's just the name it is. And pedestrian dead reckoning has 2 main ingredients. First is step detection. Second is direction of movement. So the first thing we need to do is we need to detect steps. And we can use the accelerometers in a phone to detect basically the shape or bump caused by a step. So you saw me walking, and I could exaggerate this, and my phone goes up and down, and you can see this in the axle. And fitness trackers have been doing this for a very long time, very successfully. In our case, it's a little bit more challenging, because remember, we talked about coverage. So it's not only when I'm holding this phone in my hand, but it's also when this is in my pocket, again, or it's in my purse, or in my backpack. Has to work as well, makes this problem a little bit more challenging. But let's focus on how we get that change of direction, because that's even more challenging. There is the obvious solution. We use a compass, right? And let's see how well this works. This is me holding a regular good compass in my hand flat. And just look at what this compass does. And I'm walking in a straight line here. The thing moves 90 degrees, 180 degrees, goes back, does a 360-degree turn. Okay? This is not a broken compass. This is a really good compass. What's broken is the magnetic field in this environment. That's our office building, and that just has a lot of steel, and steel influences the magnetic field. There's nothing that a phone could do, or there's nothing wrong with your phone if its compass shows the wrong direction or another direction than you expect. It just shows the direction of the magnetic field. That's what it's supposed to do. So compass alone is not going to fix this problem. The compass or the magnetic sensor is part of it, but we need to combine it with inertial sensors. And using inertial sensors to compute what's called attitude is the same thing, basically, that's done in a spacecraft. So in a spacecraft, a guidance computer needs to know how the spacecraft is oriented in space. So that has nothing to do with its position, where it is. It's only how it's oriented. And figure this out over time. And that's actually a really, really hard problem, and it's almost literally rocket science. So it's no surprise that the team that drives this pod has not only great software engineers, but a lot of aero-astro engineers who are really specialized in this. So let's say they do a perfect job. And attitude is computed as good as it can get. We're still facing a problem. We still have to deal with multiple hypotheses. And by now, you're used to this top-down view of me, and I want to show what's happening there. So this is me. Again, I have my phone in my back pocket, and I'm going to transition to this one because you see it a little bit better there. And I'm first going to take that path A, which is this slight right turn. And what happens there is my phone made a 90-degree turn to the right. I hope that's clear. Phone was like this, and then walked like this. It was a 90-degree turn. So that's possibly an explanation of what we saw on the sensors. Michael did this right turn. Another explanation is Michael actually didn't do a right turn. I just walked straight, put the phone to my ear. That's also a 90-degree turn. And we have to deal with these two possible explanations of what we see in the sensors. And we actually have to deal with a lot more hypotheses than just these two. And this is what we do. So yes, thank you. Let's keep the video there for a second. What we see here, it's again a bird's eye view. By now you're used to it. It's just not just on me. It's onto a building here in Mountain View. It's just an office building. And we see Martin actually on the parking lot. This is where this blue dot is. And there was a really nice GPS fix out there. And all these green colored dots represent hypotheses of where Martin might be given that particular measurement. And what we will see is Martin walks into this building, and I will point out what the GPS does. Namely, it's going to be stuck at the door. You will see this when we pause the video. And let's see how this works. Roll it, please. Thank you. So we switch to just the building outlines to make this more clearly visible. This blue line shows the trajectory that the location we computed followed. And if you can stop it again here, please. Thank you. So this large gray circle is the GPS measurement. If we look really closely, and I apologize, it may be a little bit hard to see, this small gray dot, that's still stuck at the door. So the GPS was not able to get enough signal to get a location fixed that is correctly inside of the building. It's just stuck at the entrance. And we have to deal with this, and we do this, of course, by using the PDR, the pedestrian dead reckoning, and we're using the strength of the Wi-Fi signals in there. So if we continue this, please. Resume the video, please. We see how nicely this trajectory follows Martin's path. This small deviation in the middle is actually in the hallway. So this is precisely picked up by this trajectory. Okay? Yeah. So we saw how we computed this blue dot from all these hypotheses. And how this surfaces to the user is going to be shown in the next video. So that's one more time, we see the same building. And we took a video of the blue dot as it shows on Martin's phone. And we see how and this is sped up by 10x. Okay? It's really amazing how everything comes together here. PDR, Wi-Fi, GPS, tracking all these multiple hypotheses and attitude. And the sped up video is a really great way to analyze this. So we see how the transitions happen from outdoors to indoors, how some jumps occur, of course, indoors. That's really accelerated or exaggerated by this sped up. Actually, can we see it one more time? Because I would like to point out the nice transitions from outdoors to indoors. Thank you so much. So that's from the parking lot, and then we enter the building, and that goes really smoothly. This was this small turn that we had. Goes well. And again, this building has no dedicated infrastructure, no surveys have been taken there or anything. This is just organic location as you will get it in there. So thank you so much. Thank you very much. So a lot of engineers did a lot of work there, and the really good thing is you don't have to do it, because Martin now is going to tell you how to use it. Thank you.
Thank you, Michael. You heard a lot on how the Fuse Location Provider works under the hood and what it takes to get a good location estimate. We barely scratched the surface, but you can already get a sense that building all this takes a lot of work. The good news is, everything that you just saw is readily available and super easy to use. We do all the underlying work for you, and you can easily access it via the Fuse Location Provider API. But we are not only working on the algorithms. We also perform extensive testing to make sure that good location is available across device types and at different places around the world. You can imagine that the environment in downtown Tokyo, maybe in a subway station, is very different from downtown Mountain View, here in downtown Mountain View. On the image to the right, you can see one of the many driving tests that we perform. And a big shout out to this place to our testing teams around the world who make this possible. One of the best parts of using the Fuse Location Provider in your application is that you can continually take advantage of the improvements that Google makes, both in hardware adoption and algorithmic improvements. These improvements become active in your apps without any code change, just via updates of the Google Play services. It just gets better and better automatically. Next, we will talk about how to use the Fuse Location Provider API. So today is Bike to Work Day, and you might have noticed lots of Googlers rolling in the morning. And to make it even more fun, let's build a simple app that celebrates us every time that we passed half a mile. And let's switch gears a little bit and dive into an actual code example. First, we need to make location available to our app by requesting the necessary permissions in the manifest. In this case, we use access find location as we require high accuracy location to determine the traveled distance on the trail. Keep in mind, you should only request the location accuracy that is required for your use case. A weather app, for example, should already get sufficient information by using access course location here in the manifest. Next, we get an instance of the Fuse Location Provider client, which is our main point of interaction with the Fuse Location Provider. We then create a location request to define the characteristics of how often we want to receive locations and what the priority should be. One dimension that we haven't talked much about yet is power. While we try to use as little power as possible when designing our algorithms, estimating a location per se requires power to run the sensors and radios and to perform the necessary calculations. This means that it is also in your hands as app developers to affect on how much power is used by your app when it is using location. So let me highlight these two lines, which can strongly affect how much power is used. In the first line, set interval defines how often our app wants to receive location updates. This obviously determines how often a location is calculated. So the higher this number, the better in terms of power usage. In our example, we use 5,000 milliseconds or 5 seconds, which is actually a pretty fast rate. You might set it to 500 seconds or even longer for your use case. In the second line, we set the priority of the location request. Priority high accuracy means that we request the best possible location using all sensors that are available. The opposite value would be priority no power, which only receives locations that are already available on the system for other purposes. So again, by setting these two values, you can influence how much power is used for location computation. In the next step, we define what to do when a new location is received. For this, we create a new location callback object and override the onLocation result method. Once we receive a location callback, we update our travel distance with is past another half mile. Once we cross the threshold, we play a hooray to notify the user and push them over the next half mile. The last two methods are obviously not part of the FusedLocationProvider API, but have to be implemented specifically for our app. Now we put everything together. When our app is resuming, we start to receive locations via the start location updates method. In that method, we request location updates using the objects that we just created. The location request, which defines the characteristics of our request, and the callback object that defines what to do with the new location. Finally, we want to stop location requests if the app is not used anymore. If onPause is called, we stop location updates by removing them from the FusedLocation client. So these were the basic steps that I needed to use FusedLocationProvider API. Those of you who are already using the FusedLocationProvider probably noticed that there are no API changes. The improvements that we made are all under the hood and have not affected the API. There are some changes, though, to the location permissions in Android Q, especially for apps that access location in the background. And you can find more information in the session updating your apps for location permission changes in Android Q. It already took place yesterday, but you will find the recording on YouTube. I mentioned it earlier already in this session. Any updates to the FusedLocationProvider will automatically be available to your apps. Here's a list of the major sources of location quality that we plan to add in the near future. First, we will, of course, continuously improve the underlying algorithms and models that are used in the location engine to improve the quality of location and reduce the amount of power that is consumed. Second, we will apply new improvements that are made around satellite navigation systems and make use of the availability of more nuanced data from the chipset. Of course, there's not only GPS, but also other global navigation satellite systems, abbreviated GNSS, like Galileo, GLONASS, or Baidu. These multiple constellations are already supported by newer phones, and with a growing number of satellites that are in view at a given location, the quality of satellite-based location information gets better. The third major improvement is Wi-Fi round-trip time, or RTT. Wi-Fi RTT is a new technology that is already supported by the Android platform since the launch of API 28 last year. As the name says, RTT uses the time that a radio signal travels between a fixed access point and a mobile device. This time is used to determine the distance between the two, and from that, a location can be derived. This is very similar to how satellite navigation systems work today and provides much better accuracy than existing Wi-Fi localization systems, which are based on the received signal strength. With more and more access points supporting the RTT protocol, for example, when rolling out the new 802.11ax high-performance standard, its availability will increase over time. To recap, here are the main points again that we talked about in this session. First, we looked into what makes a good location and introduced the 4 dimensions of accurate, smooth, ubiquitous, and instant location. Second, we took a peek into how we in the Android team actually compute a location on device and saw some of the components that run under the hood of the Fused Location Provider. Third, we looked into how you can benefit from our work and use the Fused Location Provider in your app while preserving battery life. That's all that we have today. You can find more information in the developer documentation at developers.google.com, which is helpful tips around the usage of location APIs. If you have any questions that you want to ask us personally, we'll be outside of the tent to your left. And as already mentioned, there's a talk on the Android emergency location service at 2:30 today on stage 1, which we highly recommend. Thank you very much, and carry on building great apps with location.